Hey, hey, it's Dr. J. Back again for the conclusion of section 5.3. Today we're going to do some applications, in particular in computer science. We're going to talk about binary numbers, octal numbers, both of which we've seen before, and then there's a new one today called the hexadecimal numbers. Recall, binary refers to its base. It's base 2. Octal numbers are base 8. And the new one we're going to learn today is base 16. We'll get to the base 16 in a minute. Let's talk about the numbers that we've already been discussing, binary and octal. So one of the reasons why we use the octal number system is binary numbers can be difficult to read. If you see a binary number like this, most human beings just see 111, 0011, 0111, and it's very difficult to understand, what does this number actually mean? Is this 50? Is this 100? Is this 2000? It could be, 43. We don't know. It's very difficult for us to read. It's also difficult to convert and tedious. It's not really difficult. Tedious is a better word. It's times consuming to convert to base 10. What we call decimal numbers, base 10. So we'd like to use a base that is easier to convert into binary, or from binary to that particular base, and a base that's easier for us to read, so when we see the number, we have a better idea of what that number means. And so for that reason, we use the octal number system, which uses the symbols 0 through 7. So these are symbols that we're familiar with, ones that we can calculate in our heads, and it doesn't take up too much space. It's very compact. Yeah, binary numbers take up a lot of space. Even for a small number. For example, if you wanted to write the number 17 in binary, 17 in binary. So base 10, 17 converts in binary to, it looks like 10,001 in binary. 17 is not a very big number, but look at how much space it takes up in the binary number system. Yeah. This would mean 1 times 2 to the 4th, that'd be 16, plus 0 times 2 to the 3rd, plus 0 times 2 squared, plus 0 times 2, and then plus 1. So this basically means 16 plus 0 plus 0 plus 0 plus 1, and that's how it converts into 17. But still, it takes up a lot of space to write even a small number like 17. Right? But look in the octal number system. Yeah? 17 does not take up much more space than the number that we currently use as 17. Watch. So we have 0 through 7. The number that looks like 10 is actually 8. Yeah. So 9, 10, 11, 12, 13, 14. 14 looks like 16. I think I might have got off a little bit. 8, 9, 10, 11, 12, 13, 14, 15 looks like 17. So 16 looks like 20. Yeah. And so the number 17 in base 8 is still relatively compact. Yeah, it doesn't take up much more space than writing what we already wrote as 17. So both of these numbers mean the same thing. They both mean 17. Okay. So at least that's the motivation for why we're using the octal number system in the first place. I thought about this sort of as a child. If you had no thumbs, so if you were born with no thumbs, or if maybe all humans had no thumbs, or if we just had 4 fingers on each hand, however you want to think about it. I guess you could be born with no pinkies as well. But either way, I just think it's easier to hold in my thumb like this. This would be how an octal number system would work. You would count, you would only have 7 non-zero digits. You'd have 8 digits altogether. And then when you got to 8, the symbol that previously looked like 10 would be 8. You could get pretty good at this pretty quickly. I'd say by the time you're 5 years old, you'd be an expert at counting in this octal number system. So let's look at some binary numbers and some octal numbers and some decimal numbers and get an idea of how they work and why the octal number system might be our candidate for calculating here. So I have here a list of binary, base 2. I have octal, base 8. And I've got the decimal, traditional, base 10. So we've got our different number systems. The one that you're very familiar with is the base 10 number system. Then I have the octals. I'm writing them as 2-digit numbers. That's because when you enter a number into a computer, you have to take up as many digits as you have space. So if in this particular example, I'm using 2-digit numbers, so even something like 0, I would have to represent as 2 zeros. Similarly, in binary, it would take 4 digits to represent the number 15. Yeah, you'd have 4 different digits. In computer language, each digit is called a bit. These are what we call bits. More on bits later in this lecture. For now, let's just look for a relationship between the octal numbers and the binary numbers. Now, you already have a method for converting. It's, again, quite tedious if you remember. If you look back at some of the other videos, you have to multiply by 8, and then you have to multiply by 8 squared, and then 8 cubed, and so on and so forth. I'm not going to be going over that again today. What I'm going to show you today is an interesting pattern that you'll notice by looking at the chart here. By the time you get to 7, look what happens to the binary digit over here. The binary digit goes from 0, 0, 0 to 1, 1, 1. Yeah? You can basically ignore this whole first column of zeros and just look at the pattern. 0, 0, 0, and then 0, 0, 1, 0, 1, 0, and then it looks like 0, 1, 1, and then it looks like 100, but again, 100 really just means 4. It looks like 100. And then notice how it cases over here. This is what we call the carryover. It starts again with 0, 0, 0 when you get to 8, or the octal number 8, which looks like 10. So this is a clue. That's our clue that conversion is going to be much easier in this particular base. Okay. So we're going to be able to memorize, or at least maybe have a little reference guide that I made, of all the digits from 0 to 7. And then look how it carries over. It's still going to be 0, 0, 0. It's the same pattern. 0, 0, 1. Look, same 0, 0, 1. 0, 1, 0. Again. And notice we call that the carryover. The carryover means that we've just moved over to the next column and then added the same digits the same way that we do with the decimal system. Look, the decimal system works the same way. You don't memorize the symbol for 25. You just put a 2 and then a 5, right? Because that's the carryover. Well, in binary, you're going to put a 1, and then that's the carryover, and then you carry over the same pattern from the previous 7 up to 7. Okay. So I made a larger version of this that we can use for this demonstration here. I don't need the decimal numbers anymore. I think you know all of the decimal numbers. Those are what we often refer to as just regular numbers. Let's see if I can get a little bit more space for you guys to see. Sorry about that. Okay. So we've got our binary, we've got our octal. You could memorize this list. It would probably only take you 10 minutes to memorize it. Or not. You don't have to memorize it. If you forget this list, you can just have it handy, or you could reproduce it relatively quickly. 0 is 0, 0, 0. 1, right? Suppose you forgot the list and you're like, oh no, I don't know how to do 6, right? How would you write 6? Well, you know how to write 0, right? You know how to write 1. You just go backwards and kind of reproduce it. So that must be 2, yeah. That must be 3, and it'll only take you a minute to figure out how to write 6, right? That would be 4. See the pattern? It's the same pattern that you already know. You're just only using the symbols 0 and 1. That would be 5. Okay, so that would be 6. And I wasn't looking, but let's see. Yep, I got it right. See, it looks like 6. So even if you don't have the cheat sheet, if you want to call it that, you could easily reproduce it if you needed it. Okay, so let's see an example. Example 1, convert the binary numeral, or you could say base 2 number, to octal, base 8. Okay, so let's convert this to base 8. So we're putting them in groups of 3 bits. Right? Each digit's called a bit. So groups of 3. So I want 3 bits each. Right? Each digit is called a bit. It's either a 1 or a 0. A bit is either a 1 or a 0. That's what we call a bit. If there are any, if you can't make a 3-bit, then just add the zeros if necessary. You can add as many zeros as you need. You'll never need to add more than 2. So sometimes you won't have to add any. Sometimes you'll have to add 1 0, and the worst thing that will happen is you might have to add 2 zeros. Okay. And now we just look at our binary here. We have 0, 0, 0, 1. That is 1. That's the octal number 1. 0, 0, 1. That's why I have to have these extra zeros here in my list so that I can match those up. 0, 1, 1. 0, 1, 1 is 3. 0, 1, 1 is 3. And 1, 0, 0. 1, 0, 0 is 4. So therefore, this number is 134 base 8. That's our octal conversion. Much faster than computing it the old-fashioned way, which would be to multiply by powers of 8 and piece together this long sequence of additions and multiplications. It's a much faster way. Okay. Keep in mind that this number does not really mean 134. This is 134 base 8. But at least it's a more manageable number. It's compact. If I wanted to then convert this to base 10, that would be a whole nother lesson. But today I'm just going to talk about going back and forth from the binary to the octal. Going the other way is just as easy. Example 2. Convert the octal numeral three, 5, 6, 2, again base 8, to binary. Again, the base just indicates that it's an octal number. I like to cross that off so I don't accidentally put an 8 in my calculation. So each one of these digits in octal is going to turn into a 3-bit number . 3 bits each. So each of these boxes is going to contain 3 bits. And you can either memorize these or just use this as a reference. So 3 is 0, 1, 1. Okay. 5 is 1, 0, 1. 6, 1, 1, 0. And 2, 0, 1, 0. And that is your conversion. If you have a leading 0, you're going to omit from your final answer. So your final answer, omit that 0 and just say 1, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0. And this would be your base 2 binary representation of this octal number. Okay. So octal works pretty good. Yeah, it's going to be very easy to convert back and forth. You only need to know these 8 different conversions, which is really only 7. Because notice 0 and 0, you don't really have to memorize that one. You also don't need to memorize 1. So the way I think about it is there's only 6 that I have to memorize. 2, 3, 4, 5, 6, and 7. Nobody really has to memorize 0 and 1. Those always remain the same. So at least there's that. There is one problem with this process. You might have noticed it over here. Yeah. I'm not going to be able to represent, well, let me back up a little bit. Let's talk a little bit about bits and bytes. Computers like to bundle their bits. A bit is either a 1 or a 0. Yeah, that's in binary. Over here in the binary system. A bit is either a 1 or a 0. And computers like to gather them together. 8 bits equals 1 byte. Yeah. So the way a computer works is it takes these symbols that are either 1 or zeros and puts them into groups of 8. This is called a byte. 1 byte. So when you look at your phone, and your phone says, I don't know, 64 gigabytes, that means 64 billion? Let's see, kilo, mega, giga. Yeah. So 64 times a billion bytes. So if your phone or your computer or something, your hard drive has 64 gigabytes, which, I mean, these days that's actually kind of small, but when this lesson was created, that was a lot. 64 gigabytes means you have 64 times a billion of these little blocks that hold 8 bits. Okay? So let's take the number that we just did and try to put it into a bit, right? We have 0, 1, 0. This is the one we just did. 0, 1, 1. You always start at the far right. Okay? And then what do we have? 1, 0. Oh, no, it doesn't fit into a byte, right? It's too big to fit into 1 byte. I'm going to move this out of the way for now. So it's too big for 1 byte. Yeah. So where were we? Let's see. 3, 3. Let's just group them in threes here. So we would need another byte. So 8 more bits. That's 1 more byte. And then we could finish it. We could put 1, 1, 0. And so in order to represent this binary digit on my computer, I would need 2 bytes, of which you would have lots of wasted space, including this 0. This 0 here is a technically wasted space. And you can't use it for another number. And I'll tell you why. If you try to be cheap and say, well, why can't I just squeeze in some more digits so I don't waste that space? The computer won't recognize that these are different numbers. The computer would then take all of those 1s and 0s that you put into these wasted space. Suppose you're trying to fill the wasted space, and it would include it in the entire number, and then it would be the wrong number. So when you waste space, you have to leave that space empty. This would happen all the time if we use the octal system, right? So the octal system is nice. It's easy to convert back and forth, but there's a better system. A system that would go back and forth very easily. It's a multiple of 8. It's a power of 2. And it gives us less wasted space. So let's try hexadecimal to see if, so that's base 16. To see if there is less wasted space. All right, we don't want this to happen. We don't want to have a bunch of wasted space. It'd be nice if I wanted to represent a number, it either uses an entire byte, or maybe it uses 2 bytes, or maybe it uses 3 bytes, but we would like to actually fill up all of these bytes as much as possible. All right, and we might have 1 or 2 empty characters. There might be a 0 once in a while, but we certainly don't want this to happen. We don't want to have, what was that, 1, 2, 3, 4, 5, 6 bits of wasted space that we needed only to hold these extra 2 bytes. So let's talk about hexadecimal. Hexadecimal is base 16. That's the next power of 2, 2 to the 4th power. So any base that is a power of 2 is going to line up nicely with the binary system, and you're going to have this nice pattern that we saw in the previous example. So hexadecimal uses 16 different symbols. Uh-oh. What do we do when we get to 9? Yeah. We need 6 more symbols. Yeah. And that's a problem. That's the first problem we encounter with hexadecimals. What symbols could we use? I sometimes give a lab assignment where I have my students, that would be you, if we were back at school, I would have you create your own new symbols. I would let everybody create 6 new symbols. So you can go, oh, I want to make up my own symbols. You can't use symbols that have already been used before. So you could make up your own. And you need 6 more symbols that are not already there. It can be anything. Yeah, you can do whatever you like to do. The problem is going to become clear very quickly. I need 6 new symbols. I got a spiral. I've got a, looks like I'm omega. I've got a backwards L. I've got my little lightning bolt. What else could we do? A triangle. Again, I'll let you guys make up your own 6 new symbols. Right? I need 1 more symbol. How about $? Okay. Let's make it easier to read. I'll just put a 1-bar $. So these are my hexadecimal number system, right? And this is a legitimate system. As long as you have a total of 16 symbols, the first 10 symbols are the the Hindu Arabic numerals. I almost decided to use X and IV and the other Roman numerals, but I decided to just make up my own symbols. What's the problem with this? I don't know if you can clearly see what I see. How am I going to know? I'm going to have to memorize that this symbol means 10, and this symbol means 11, and this symbol means 12, and this symbol means 13, this symbol means 14, and this means 15. Now, that might be easy. You might be able to memorize that, but then you're going to have to remember what order they're in, right? It goes spiral, omega, backwards L, lightning bolt, triangle, $, right? Now, you've spent your whole life since you were 6 years old memorizing these symbols. So if I were to put this out of order, right? If I were to put the traditional numerals out of order, you would immediately recognize it because you've been doing it since you were 5 years old. You go, wait a minute, that symbol's in the wrong place, or that symbol's in the wrong place, right? Now, I've tried this before. Try to memorize these 6 symbols and then erase them, and then see if you can write them down in exactly the same order again. Chances are you're going to get some of them in the wrong order. Now, I'm intentionally putting some of them in the wrong order. All right, so there's the same 6 symbols. I did manage to memorize them, which, by the way, I just made those up. So that's a demonstration in instant memorization. I made up 6 symbols, I erased them, and then I tried to reproduce those exact 6 symbols again. I would say I got pretty lucky. My spiral didn't come out very good, but whatever. Okay? It's a bad idea. That's what the point I'm trying to make. Making up your own symbols, although it is legal, It's legitimate. You're making up a number system, or you're going to use a number system. It's better if you use a symbol, or at least 6 symbols that you've known since you were a child. What symbols do we learn when you're 5 or 6 years old that go in order that you already know, that you'll never forget, you don't have to memorize, and if you got them in the wrong order, you would recognize it? Other than numbers, I hope that you all agree, the ABCs are the next basic. I just wrote C. A, B, C, D, E. We only need 6, so we're going to use the letters A, B, C, D, E, F. And then if I get these in the wrong order, you're going to know it. You're going to go, wait a minute, F comes after E, or D comes after C. And so if I accidentally put these in the wrong order, if you make any kind of mistake, you'll be able to catch your mistake. Okay. So keep in mind, here's your little mind cloud. A means 10, B means 11, C means 12, D means 13, E means 14, and F means 15. All right, so keep that in mind. They're not letters. These are hexadecimal numbers: 10, 11, 12, 13, 14, 15. So the number that looks like 10 is actually 16. All right, that's the subscript base to tell us it's 16. So on and so forth. The number that looks like 11 is actually 17. Base 16, the number that looks like 11 is 17. Okay. So these are the hexadecimal digits. Let's see how they line up with the binary digits. With the hexadecimal, you're probably going to need 4 digits or 4 bits. 3 is not enough, so we're going to group them in groups of 4. But that'll work nicely because a byte is 8 bits. So we can group them in 2 groups of 4. And we'll be able to have 1 byte written out like this as 2 groups of 4. And we won't have any wasted space. So 1 byte would be 2 digits, 2 hexadecimal digits. This one's a little bit tougher to memorize. So if you had to memorize this, it probably would take a little bit longer than the octal. But here's the trick that I will give you if you do want to memorize it, although you'll have this handy. You can print this out. I'll put a copy of this on Canvas, so if you want to print it out, or you can just look at it on your screen. But suppose, some of you might want to actually learn this from memory. And so if you do, this is how I learned it. I just memorized 0 through 7, which is exactly the same as the octal. So that's why it's good to do the octal exercises first. You'll notice that the last 3 digits are exactly the same as the octal. All you do is add the first digit or the first digit is 0, right? And so if you've memorized the octal, you've got 0, 0, 0. It just counts from 0, 0, 0 all the way to 1, 1, 1. And then I'm purposely hiding the other 8. And then when I flip this over, notice the pattern. It's exactly the same pattern. Same pattern as the octal. It goes from 0, 0, 0, 0, 0, 1. It counts through all the octal digits all the way to 1, 1, 1. But you just put a 1 as the first digit. So if you've already memorized the octal, all you do is add a 0 or a 1 in front of it, and that will get you all the way to F, which is all you really need to know, is from 0 to F. Again, or you can just have the entire sheet out in front of you when you do your examples or you do your homework, and you can just use this as a reference. Okay. Let's try an example. All right, so example 3. Convert the binary numeral, or I could also call it base 2, to hexadecimal. We got a delivery. 1, 1, 0, 1, 0, 0, 1, 1, 0, 1, 1, 1. Yeah, let's keep going. 1, 1, 1, 0. Might as well. I got some space. Might as well use it. So we want to group these into groups of 4. So this would actually be 2 bytes. Yeah, this would be 1 byte. This would be another byte. So altogether, this is 2 bytes. Okay, and we just do them 4 at a time. So 1, 1, 0, 1. We look at our sheet. 1, 1, 0, 1 is D. 1, 1, 0, 1, that's D. 0, 0, 1, 1. Up here, 0, 0, 1, 1, that's 3. That's 3. 0, 1, 1, 1, that's 7. 0, 1, 1, 1, that's 7. And then 1, 1, 1, 1, 0. 1, 1, 1, 1, 0 is E. And so this is our hexadecimal or base 16 number. D37E. I know it looks like alphabet soup, but that's actually a number. It's a number base 16. We also had very little wasted space because we're always going in groups of 4. All right. Example 4. You can go the other way. Convert the hexadecimal to binary. So I'll give you a hexadecimal number, and we'll go through the same process and convert it to binary. So suppose we had 4F D6. 4F D6. That's the hexadecimal. Okay. So we're going to need 4 bits for each digit. If you have any leftover space, make sure leftover space always goes to the far left. So if there's any wasted space, there might be some. This number will take 2 bits of information. There might be a little bit of wasted space. I don't know. It probably won't be much, but we'll see what we get with it. Okay. You're never going to have as much wasted space as we had with the octal. So we got 6. Okay, if you need your reference, you've got your reference here. 6 is 0, 1, 1, 0. That's 6. You got D. D is 1, 1, 0, 1. That's D. You got F. F is 1, 1, 1, 1. I always memorize that one. Yeah. 1, 1, 1, 1, 1. And then 4. 4 is 0, 1, 0, 0. So we only wasted 1 space. Wasted space is a 0. Any collection of zeros to the far left is considered wasted space. So we only wasted 1 bit. Yeah, which is pretty good. If you, I mean, in computer terms, wasting 1 bit for a number this size is not too bad. So in your answer, I don't want to see the wasted space. So just list out all the digits. 1, 0, 0, 1, 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0. You're not allowed to throw away zeros at the far right. You can only throw away zeros that live to the far left. Those are wasted space. So this is a 2-bit number. That's how much space it took. Sorry, 2 bytes. I said bits when I meant bytes. It is 15 bits or 16 bits with 1 wasted. We wasted 1 bit out of the 16 that we had. So you might think to yourself, oh, is this over yet? Well, yeah, it's almost over. Is this a good enough application for computer science majors or people that are interested in computers in general? Well, I hope so. I hope I at least gave you a little motivation for why we're doing this. But there is one thing that a lot of us use hexadecimal numbers for quite a bit. And you might not even realize you did it. I know I did it today to set up this video. There's a green screen behind me that's enabling me to appear down here in the lower right-hand corner of the video. And in order to get this green screen to match the color of my screen, I had to use hexadecimals. So one of the main applications is hexadecimal in computer graphics. For color. Yeah. It's called the RGB color scheme. Yeah. R stands for red, G is green, and B is blue. And so what your computer does is it only uses these 3 colors. It uses red, green, and blue, and it sort of mixes them all together here, and it gives a combination, almost like mixing paints when you were in, elementary school or art class and you're mixing your different paints on your palette. You have a combination of the three colors is specified by a hexadecimal number. Or numeral, if I want to be really precise. All right. And so that would give us the exact blend. I guess you can call it a blend of red, green, and blue. And just the right amount of red, green, and blue. However, depending on how much of the red and how much of the green and how much of the blue is given as a hexadecimal number. So if you had something like example 5, a hexadecimal number such as 70C2E4 represents a color in the RGB system. Convert each color to decimal base 10 to see how much of each color is being used. So the first two digits represent red. That's your R. Red. I should probably use the word red because the letters might be. And then green is second. And then blue. And so this number, 70C2E4, is a blend of red, green, and blue, which shows up on my screen as a particular shade of, it looks sort of like green in this particular scheme. This is my green screen setting for the screen behind me. Okay, so that's how much it took to get me to, or to get that to disappear so you could see me through this. I'm hoping you can see me. Can you see me? Can you see me? Now, you could convert this first to binary. All right, so we got E4. E4. What does E4 mean? Well, let's see. What does E4 mean? Let's do one color at a time. So we got 1 byte. Each one of these takes up 1 byte, or 8 bits. So E, here's my cheat sheet here. E is 1110. Right. And 4 is 0100. So what does that mean? In this is in base 2. This is in binary. Okay. So how much of the blue are we actually using? Well, we're using E4 of it, which is this much blue. This is how the computer would read the number. if you wanted to tell a person, how much, what's the quantity of that blue on the color scheme, yeah, it's like a wheel or a sort of a sliding bar of how much you're going to use. You could just go like horizontally as well. So to convert this into decimal, and again, this is for blue. Let's count. We have 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6, 7. So that'd be 2 to the 7th plus 2 to the 6th plus 2 to the 5th. There is no 2 to the 4th. There is no 2 to the 3rd. There's 2 to the 2nd. So that would be 2 to the 7th. 2 to the 7th is 128. If you have to, you can use your calculator. 2 to the 7th power, and you get 128. I think you can do the rest of these by hand. 2 to the 6th is 64. 2 to the 5th is 32. And 2 to the 2nd is 4. Remember, there are thousands of color combinations, or I think it's hundreds, but there's thousands altogether. Each one of these is 256 possible combinations. $256 different combinations for each one of these colors. So there are 256 blues. All right, so which blue are we using? We're using E4. That comes out to be, I'm going to go ahead and use my calculator for this, although you don't really have to. 128 plus 64 plus 32 plus 4, 228. So that's what E4 means. All right, so out of 256 shades of blue, E4 is the 228th shade of blue. We still need to do green and red. So let's do green. C2, remember we need 4 bits for each digit in hexadecimal. So C is 1100 and 2 is 0010. So that is the color C2, that is a shade of green in binary. To convert it to decimal, each of the ones represents a power of 2. So we have 2 to the 7th plus 2 to the 6th. There is no 2 to the 5th, none. No 2 to the 4th, no 2 to the 3rd, no 2 to the 2nd. And then there's 1 2 to the 1st. The last digit means whatever it is, so that last digit means 0. So that's 128 plus 64 plus 2. 128 plus 64 plus 2. It's 194. And that would be base 10, the decimal number. So C2 would be color 194 out of 256 possibilities for each color. Yeah, there are 256 possible combinations for each color. So this is green 194, or we would just say C2. Right? You see how much more compact it is? In terms of hexadecimal, you only have to say C2. I would like color C2, from the color wheel. Finally, let's do red. Red is 70. That's not an O, that's a 0. So red is 70. So when we convert that to binary, each hexadecimal digit is 4 bits. Altogether, it should be 8 bits, which is 1 byte. All righty, so here we go. 70. So I got my cheat sheet here. 7 is 0, 1, 1, 1. That's 7. And 0 is 0, 0, 0, 0. Remember, when you're entering your answer, you cannot omit zeros on the right-hand side, but you can omit any wasted space here. So that 0 would technically be wasted space, and your answer would just be 1, 1, 1, 0, 0, 0, 0. That would be your answer, base 2. Okay. So what does this mean in decimal? Well, you have to calculate it out. Remember, now this is 2 to the 7th, which we omitted. So this would be 2 to the 6th plus 2 to the 5th plus 2 to the 4th. Everybody else is a 0, so they actually mean 0. So 2 to the 6th is 64. 2 to the 5th is 32. And 2 to the 4th is 16. So 64 plus 32 plus 16 is 112. 112. So the color 70 is 112. Just to summarize this answer, the left-hand column here is your hexadecimal, and the right-hand column is your ordinary decimal, base 10. Okay, well, there it is. That's your application of binary, octal, and hexadecimal numbers. Dr. J signing out. See you tomorrow.